In the last video, we saw how we use four quantum numbers, four integers, to specify the state of an atom. And these are the four quantum numbers which do that. N is called the principal quantum number, and it has allowed values of 1, 2, 3, etc., and is an indicator of the size of the atom. And also, N appears in the equation for energy. So N is also, each N value corresponds to a certain energy level. The next is L, which is the angular momentum quantum number. And for a given N, L can have values 0, 1, 2, 3, etc., all the way to N minus 1. So L can never exceed N. And then within a certain L, we have the third quantum number, ML, which is the angular momentum projection quantum number. So this is the, it's a measure of the component of angular momentum in the z direction. And that can have values from negative L to positive L, all the integers. And then finally, we have the MS, the spin projection quantum number, which indicates the z component of the spin of the electron in the atom. And that can only have two values, negative 1/2 or positive 1/2. This is called spin down, and then this is called spin up. So it's basically spin up and spin down means that whether the electron is spinning clockwise or counterclockwise. So if you start with a simple atom like hydrogen, which only has one electron, then it's very easy to guess where, in what state would that be. There's a law of nature that all states, all systems try to be in the lowest possible energy state. So everything tries to minimize its energy, which means the hydrogen atom will be in the ground state or n equals 1. And if n equals 1, then we know the rest of the quantum numbers, like L would be 0, ML would be 0, etc. However, when you get to larger atoms, atoms which have more electrons, then we need to understand what its state would look like. The obvious guess would be, well, all of the electrons, let's say oxygen, if it has 8 electrons, we know we will guess that since systems try to minimize their energy, all 8 of those electrons will be in n equals 1 state. And that's how you can minimize the energy of the oxygen atom. However, nature is not as simple as that. And that brings us to what's called the Pauli Exclusion principle, which tells us about the states of multi-electron atoms. If electrons have more than one atoms, then what kind of configuration of quantum numbers do they have? First of all, physical and chemical properties of elements are related to number of electrons in its atoms. And that number is represented by Z, called the atomic number, which is also equal to the number of protons in the nucleus. For ordinary matter, number of protons and number of electrons are the same. Now, Pauli exclusion principle tells us that no two electrons in a system can be in the same quantum state. They cannot have the same set of quantum numbers. Now, this principle applies only to particles known as fermions. Fermions are fundamental particles whose intrinsic spin is a half integer So spins of 1/2, 3/2, 5/2, etc. are called fermions. So this principle applies only to fermions, and it turns out that electron is indeed a fermion. It has a spin of 1/2. So clearly this would apply to electrons in an atom as well. And that imposes the idea that no two electrons in a system can have the same set of quantum numbers. It imposes constraints on number of electrons in a certain energy level. So for example, if you consider the n equals 1 state, for n equals 1, we know that L and ML are 0, so the middle quantum numbers are 0. However, you can create two distinct states by having one spin up and then one spin down. So that means in the n equals 1 state, you can accommodate up to 2 electrons, no more than that. One electron will have this state, the other electron will have this state. If you have a third electron, I think beryllium is the next element, which has 3 electrons. So if you have a third electron, you would have to go to n equals 2 state, because n equals 1 state, you can only have these two possibilities. So you go to n equals 2 state, and then you start filling those up. The terms shells and subshells are used. The value of n indicates a shell. So basically, you can think of it as orbits. N equals 1 shell, n equals 2 shell, etc. These are all n equals 1 state, or n equals 2 state, n equals 1 orbit, etc. So n is the shell into which a limited number of electrons can go in accordance with Pauli exclusion principle. The probability cloud with the lowest L value is closest to the nucleus. Lower value of n means the cloud is closest to the nucleus, and it's most tightly bound to the nucleus. When shells fill, they start with L equals 0, and then L equals 1, 2, etc. So just as n, value of n indicates the shell of an atom, similarly, the value of L is referred to as subshell. So within a shell, you have subshells. There are certain symbols used for different possible L values. So L equals 0, for example, is called the S subshell. L equals 1 is P subshell. L equals 2 is D. L equals 3 is F. And then beyond that, you just go in alphabetical order. 4 is G, 5 is H, etc. Now, these first 4 letters might appear to be like a weird choice, Y, S, P, D, F. This is related to how this whole idea of subshells originated. It was based on empirical evidence. It was based on experimental observations. There was no theory behind it. So the idea of subshells came out of atomic spectrum, observation of atomic spectrum. And the quality of the spectrum, the nature of the spectrum is reflected in this choice of letters. I know S, for example, it stands for sharp. D stands for diffuse. I forget what P and F are, but that's where it's a historical artifact. So shells and subshells together are represented by N and L, the values of N and values of L. Number of electrons in a particular subshell is indicated as a superscript. So for example, if you're talking about n equals 2, a principal quantum number having a value of 2, you will write the 2 here, and then you will indicate the value of L, what subshell you're in. So P here means we are talking about L equals 1. And then a superscript of 3 means there are 3 electrons in that subshell. So this is a common notation to represent the state of an atom. And this is called the spectroscopic notation, Again, coming out of the observation of atomic spectra. Counting the number of possible combinations of quantum numbers allowed by the exclusion principle, we can determine how many electrons can be accommodated in each shell and subshell. So for a given L value, there are 2L plus 1 possible ML values. How do we know that? Remember, for a given L, ML has values from negative L plus 1 to positive L plus 1. And then for each case, you have 2 possibilities of the spin up and spin down. So you get ML value. So there are 2L plus 1 ML values. And then for each one, you have 2 MS values. So each L value can have 2 times 2L plus 1 electrons. Just to go back and to show you where that 2L plus 1 comes from. So these are the possible values of ML. So if you count them, there are L negative values, and then there are L positive values, but then there's also a 0. So that's where the 2L plus 1 comes from. And then for each L, you have 2 possible, for each ML, you have 2 possible MS values, spin up and spin down. So this gets multiplied by a factor of 2. So what that means is each N value, which can have N minus 1 L values. And so if you do a summation over all possible L values going from 0 to N minus 1, you get a series which adds up to an N squared. And then again, spin up and spin down. So basically what this tells us is that a shell, a certain N value, can accommodate up to 2N square electrons, 2N square electrons. So if you have a shell, say N equals 3 shell, then it can accommodate 3 squared is 9 times 2 is 18. So it can accommodate 18 electrons and so on. Let's look at problem number 44. Which asks how many electrons can be in the N equals 4 shell. So starting with that, N equals 4. And so if you use that there are 2N square possible electrons, so you plug in 4 for N here, and that gives you 32 electrons. So you can have 32 electrons in that shell. And then part B asks for what are its subshells and how many electrons can be in each. Well, for N equals 4, these are the possible values of L, 0, 1, 2, and 3. L equals 0 means we're talking about the S subshell. So that can have 2 times, using that formula, 2 times 2L plus 1, this one, we get 2 times 2 times 0 plus 1, which is 2. For the P subshell, L is 1, so we get 6. For D, L is 2, so we get 10. For F, L is 3, and so we get 14. And you can see that if you add up all these number of electrons in each subshell, it does add up to 32 for the whole shell. Okay. So how do the shells fill as you get to larger and larger number of electrons in an atom? So let's look at table 30.3, which is this. And it shows the various configurations, quantum number configuration for various elements. So start with the smallest n and smallest L. So, well, H, hydrogen, has only 1 electron. So that's going to be in n equals 1, L equals 0 state, so 1s. And there's obviously just 1 electron. So the ground state of hydrogen is represented by 1s1. Ground state of helium, which has 2 electrons. And remember, the 1s subshell can accommodate 2 electrons, spin up and spin down. So both of them will be in the 1s state. When you get to lithium, well, I misspoke earlier. I said beryllium, but it's actually lithium that has 3 electrons. 2 of them will be accommodated in 1s2, but then that's it. So for the third electron, you would have to go to n equals 2 state. And within the n equals 2 state, you start with L equals 0. So that is 2s1. And then you get to beryllium, which has 4 electrons. It's customary to not repeat this 1s2 because you know that that's what it's going to be for all of the first 2 electrons. You just write down the higher subshells here. So beryllium has 2 here, and then this 2s can accommodate 2, so both of those go here. When you get to boron with 5, you fill these 2, and then the leftover electron will go to 2p1. So after you have filled L equals 0 subshell here, you go to L equals 1 subshell. And that's basically how you fill up the various shells and subshells in multi-electron atoms. So you start with the smallest n and smallest L, and then as Z value increases, as the number of electrons increases, there are certain exceptions which arise. And so in actuality, the atoms are somewhat more complex than what this picture depicts. So the filling of the shells is not always this linear, this straightforward. What happens is in multi-electron atoms, the electrons, in addition to interacting with the positively charged nucleus, they also start to interact with each other. And that complicates the nature of L and N values. So one of the consequences of that electron-electron interaction is that some L values might have more energy than you would expect compared to other L values. So, for example, I was saying earlier that in terms of energy, L equals 0 will have the least energy, and then L equals 1, and then L equals 2. But in some cases, because of the electron-electron interaction, it doesn't go in that linear fashion. So there are some exceptions to this. Notice that potassium 4s1 fills before 3d. Here's potassium. So if you look at, like after 3p6, you would expect 3d, but actually the last electron ends up in 4s1 state instead of 3d. So there are some exceptions. For our purposes, for this course, you don't need to worry about what these exceptions are. So the probability cloud for n equals 4, L equals 0, turns out it's closer to the nucleus than n equals 3, L equals 2. And that's the reason why this first one is more desirable, or this one will fill first than the second one. The number of electrons that you have in the outermost shells determine the chemical properties of elements. Since these are most loosely bound and can therefore participate in chemical reactions, they can form bonds with other atoms to create molecules and so forth. This is a periodic table. You can't see very well, but I'm sure you know what a periodic table looks like. So the chemical properties depend on the outermost electrons, and elements in each column here, have the same number of outermost electrons, and therefore they're all chemically similar. And as you know from other courses like chemistry, then each column has a certain name, a type of element which behave chemically very similar to each other. Okay, let's look at problem number 47. Problem 47, list all possible sets of quantum numbers for the n equals 3 shell and determine the number of electrons that can be in the shell and each of its subshell. So n equals 3. Let's first calculate how many total electrons you can have in this shell using 2n squared, so that comes out to 18. So you can accommodate 18 electrons in this shell. Now we go down to the subshells. So if n is 3, L can have values 0, 1, 2, 0, 1, 2. So we're going to go in order, first starting with n equals 3, L equals 0. If L is 0, the only possibility for ML is also 0. And then MS can always be plus or minus 1/2. So this shell in the spectroscopic notation would be the 3s subshell. I'm sorry, this subshell. And the number of electrons it can accommodate is 2, 1 for spin up, 1 for spin down. Next, we move on to L equals 1 possibility. For L equals 1, we have 3 possible values of ML, namely -1, 0, and +1, and then spin up, spin down. So this subshell will be called 3p because L is 1 here now, N is 3. 3p, how many electrons? 2, 4, 6. So 3p6. Then we go to the next possibility for the value of L, which is 2. So now ML can have 5 values from -2, -1, 0 to 1 and 2. And then each one will have plus or minus 1/2. And this would be the 3D subshell because L is 2 or D. And this can accommodate 2, 4, 6, 8, 10 electrons. So this is the total number of electrons you can accommodate. 2 plus 6 plus 10, 18, which is what we had predicted from this formula as well, from that equation. Okay, part B. Show that the number of electrons in the shell equals 2n squared, and that the number in each subshell is 2 times 2l plus 1. Well, we've already done that. 2 plus 6 plus 10 is 18, which is 2n squared. As far as showing that this expression is accurate in terms of how many electrons you can accommodate in each L value, for each L value. So if you go to 3s, which was the first one here, that would be 2 times 0. S is L equals 0 plus 1, so that's 2. And then for 3p subshell, L is 1. So 2 times 1 plus 1, which is 6. And then 3 times 2 times 2 plus 1, which is 10. And that's what we had by counting. Those are the numbers we had. Okay, problem number 49. Which of the following spectroscopic notations are allowed? So we're gonna evaluate each one at a time. So starting with 1s1. 1s1, so we are talking about n being 1 and L being 0, and it has 1 electron. Well, if n is 1, L is indeed allowed to be 0, and it can have up to 2 electrons. So this state is perfectly legitimate. It is allowed. Next one is 1d3. So n is 1 and L is 2, and there are 3 electrons in it. This one is not allowed because if n is 1, L cannot be 2 according to the constraints on the L values. For n equals 1, L can only be 0, nothing else. So the second state is not allowed. Next is 4s2. So n is 4, L is 0, and it has 2 electrons. That's definitely allowed. Next is 3p7. So n is 3, L is 1, and there are 7 electrons. N equals 3 and L equals 1 is indeed allowed. But let's see how many electrons are allowed to be in there. So we do 2 times 1 plus 1, which is 6. So you can't have 7 electrons in it. So for that reason, 3p7 is not allowed. And then the last one is 6h20. 6h20, so N is 6, L is 5. and this one can have 2 times 5 plus 1, or 22 electrons. So 20 is definitely allowed. So this last one is allowed as well. That brings us to the end of this chapter on atomic physics. Next, we will go on to, in the next chapter, we will study some basics of nuclear physics.